With our newfound ideas about reaction mechanisms, we want to actually define where reaction orders come from. So if I'm dealing with an elementary reaction, which means I know I'm dealing with a single molecular collision or a single molecular event, now orders are going to describe how many of a molecule are participating in that step. So if we use this ozone and O atom reaction, the rate is going to be based on the number of collisions. So basically there's two O3 molecules, two O atoms. So I can have a total, that gives me a total number of collisions. If I increase one of my reactants, okay, say I double the concentration or double the amount of O3 that's present, now I would have double the number of collisions, right? If I increase the number of collisions, that leads to the reaction going twice as fast. That because each collision has the same probability of being successful, more collisions, just more chances of being successful, the rate is twice as fast. I could also accomplish the same thing by doubling the amount of O atoms. Again, I'd have 8 collisions and the rate is twice as fast. So what that means is for an elementary reaction, where the reaction equation that you're writing is describing an actual molecular process, the order is equal to the coefficient of that molecule or atom in that reaction. So we have our elementary steps for this reaction mechanism that we've talked about. Let's actually come up with the orders for those. All right, so when we're given an elementary step, if we know that it is an elementary step or an elementary reaction, then we can come up with the rate law just by looking at the equation and specifically the orders in the rate law. So this is reaction or step 1. So what we can do is we can define rate 1. So the rate for the first step, we know there's going to be a rate constant there, and we're going to call that K1. We only have O3 as a reactant, and whatever the coefficient is in O3 or however many we have there, that's going to be the order. So in this case, O3 is going to be first order because there's only one of them in the reaction equation. So we can use the reaction equation. The coefficient is 1 there. So the exponent on O3 is also going to be 1. For step 2, we can define rate 2. Again, there's going to be K2. This time I have O atoms and O3 molecules. Coefficient on that is 1. Exponent of 1. Coefficient on that is 1. Exponent is going to be 1. So when we have elementary steps, when it's elementary reactions, that is no longer just an overall reaction, but you are explicitly describing a single collision between molecules. That is when the order is going to be equal to the coefficient in the equation. So because we can get the orders for any elementary step, that also lets us set up what the rate law is going to look like. Because we know that the form of every rate law is K times, our concentrations raised to their powers, their orders. And so we can get K from any sort of experiment, but we really need to get the orders from these ideas of reaction mechanisms. So what we can say is this is the rate law for step 2. We don't necessarily need to know the value of K2 because there's plenty of experiments we could do to figure out what that value is. But we would say that this is the rate law for this step. Participation 918, question 2. Obtain rate laws for each of the following elementary reactions. A, 2NO2 becomes N2O4, and B, H2O becomes H plus and OH minus. This is the second question on participation 918 due Friday, September 18th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the documents where these videos are posted. Again, obtain rate laws for each of the following reactions. A, 2NO2 becomes N2O4, and B, H2O becomes H plus and OH minus. So this idea that for an elementary process, order is just equal to the coefficient really does come from the ideas of collision theory, because these elementary reactions actually are reflecting a collision, right? The actual collision or an actual process. And so we oftentimes call this the molecularity of a process, which just means the number of molecules that are participating. So first order reactions are unimolecular. So uni meaning like one. So unimolecular is one molecule. So these would be reactions or processes where one molecule just undergoes a change. It could be something like light came in with the ozone example, or it could be something like this molecule, this reactant is called cyclobutane. It is relatively reactive with itself and will fall apart and become two ethylene molecules that we have on the right. And so there is some chance of one reactant molecule changing, right? This molecule, you can imagine, it's like colliding with its neighbors, but it doesn't have to change its neighbors. If it's, say, in a liquid, it's bouncing around, the bonds could just spontaneously break. You could imagine it bounces around, kind of collides with something, and then that bond breaks, right? That bond breaks, the molecule's kind of flopping around, and all that really requires is this one molecule. You don't have to break bonds from anything else. You don't have to collide in a certain way with another molecule, just this one molecule. And so if it's just there's some chance of each one molecule changing, more molecules means more chances. But that's why it's a unimolecular or first order process, just one molecule is participating. When we step up to two molecules, that's a bimolecular process, which would then be second order. So this is kind of the idea that we talked about previously with collision theory, that two molecules need to collide. And so in this case, you need, it's a collision of, say, NO2 and CO. And in this case, you need both reactants in order to have this process happen. It is bimolecular. You have two molecules participating. So you can have a bigger effect on the rate. You have more flexibility. Do you add more NO2? Do you add more CO? What are you trying to accomplish? How are you trying to move these around? You could also add more of both, which would increase to have a double effect, or a squared effect on the rate. That's why you get that second order effect. So when we're looking at kind of returning to overall reactions, so say the 2O3 plus the 3O2, that is an overall change. You start with some ozone, some O3, and you get oxygen molecules. When we're looking at these overall reactions, we cannot assume that the order is based off the coefficient. And that's because these orders would correspond to the number of molecules participating in a collision. So if you were to say that O3 is second order, you would be implying that there are two of those molecules participating in a collision. But that's not the case in this reaction mechanism, right? O3 reacts by itself, then it reacts with O molecules, okay? And so, when we're looking at these ideas of orders, they are corresponding to the number of molecules in a collision, and we're really just not seeing that in the reaction mechanism. And so that's why orders can only come from these elementary steps, because that's where we're actually describing molecules that are colliding with each other. These molecules are not touching each other. That's not how this reaction actually occurs. There's instead processes with two separate and distinct O3 molecules. Another question for participation 918 in this video. I bet there'll be more questions in the next few videos. See you there.